So, let us start. So, we did Herbrand's theorem. So, let us actually go back a little bit and recap those things. So, actually let us look at this. So, we had this Herbrand tree of interpretations, and essentially what we are saying is that you take firstly our Herbrand interpretation. So, this is the set of all possible interpretations, Herbrand interpretations. So, which essentially means that you take any theory that you want, you do not have any concrete representations. The only concrete representations you have are in terms of the terms defined on that signature, and these P naught, P 1 etcetera are essentially atomic predicate symbols applied to ground terms. So, which firstly implies that you do need at least a constant. So, we are always talking about a signature which if it comes without a constant, then we expand it to include a constant at least. So, that there are ground terms, otherwise the set of ground terms would be empty. So, you have a non-empty set of ground terms, and in fact, if you have even one constant, then if you have even one constant symbol, then you have an infinite collection of ground terms actually. And those ground terms apply to the atomic predicate symbols of appropriate arity, enumerate all those ground formulae, ground atomic predicates, and essentially these capital P naught, not P naught, not P 1 and so on and so forth, essentially signify ground atomic predicate formulae, ground atoms, and there are all possible truth assignments for these. So, right. So, this tree, this infinite tree, of course, you have only a countably infinite number of them. You have only a countable, your language of terms itself produces only a countably infinite collection of terms, and you anyway have only a finite number of atomic predicate symbols. So, the number of ground terms that you, ground atoms that you have is only countably infinite, and it cannot be more than that. So, the Herbrand tree of interpretations essentially gives you all gives you a power set of that. Yeah. So, it gives you all possible interpretations in the term algebra itself for all possible atomic predicates. Right, and what we showed the compactness theorem, which notice that this compactness is only for a set of closed quantifier free formulae here, and later it is only for closed formulae. Yeah, compactness of closed formulae. So, we are not really talking about formulae which are open and which have free variables and so on and so forth. So, and what we are saying is that a set of set phi of closed sigma formulae has a model if and only if every finite subset of phi has a model. In this, phi can only be countably infinite, because we are constrained by a language. So, it cannot be an uncountable set of formulae, for example. So, it is only a countable set of formulae, and there is one possibility which of having things uncountable, which I have not actually ever mentioned. The only way you could have a possibly uncountable number of formulae is actually if your signature sigma has an uncountable number of atoms or atomic predicate symbols or function symbols. If it does, or simply if it just has an uncountable number of constants, take the reals for example, I think of every real number as a constant, then I have a signature over the reals which is actually uncountable. In which case then the number of terms that you have is actually uncountable. which also means that you could therefore have an uncountable number of formulae. But let us not get into that. There, so actually, so in theory, actually this set phi could be uncountable, and provided if you have an uncountable number of terms, for example, and you can have an uncountable number of terms, for example, if you have an uncountable number of constants in your signature. But let us not get into that, we will stay with countability, and our infiniteness will always be at most countable, right. So, we proved the compactness theorem.
In the proof there is one doubt.
Yeah.
In this, how do you move from that G sco phi to a finite subset of psi?
This is because of the previous lemma, right?
This is okay, but from the we found out a finite subset of G sco phi, G of sco phi, and then the next line we claim is that there exists a finite subset of phi which is not satisfied.
Just a second. Okay, is this where you are saying there is a problem?
No, the line after by lemma, next sentence.
This finite set is a subset of a finite subset of phi that does not possess a model. If it is a finite set, then anyway it is consists of ground terms. Okay. It is given that it is a finite set, it should be a, so there should be only a finite number of so after, if this is a finite set, then you are saying that this finite set need not be a finite subset of capital phi.
No, we are saying that how come this thing comes? Can you explain it a little bit? How is this a finite subset of G sco phi? It is always a subset of some finite subset of phi.
Okay, let's look at sco phi. Sco phi is obtained from capital phi by skolemizing each of those finding Skolem functions for the existential quantifiers. There are anyway only a finite number of them, right. And when you find the set of all ground instances of these, all you are doing is you are replacing all the variables. Now, after having skolemized, they are all just universally quantified universally quantified predicates, and you are instantiating those universally quantified predicates with ground terms. Okay. And your G sco phi is essentially this, and all this is countable at most. All this is countable at most, and with the assumption that it does not possess a model means that there is a finite subset which does not have a model, and it therefore means there is a finite subset of G sco phi which does not have a model. But that G sco phi, that finite subset of G sco phi comes from some finite subset of atoms in phi, that is it, from some finite subset of formulae in phi, and they just some ground instances of those, some finite set of ground instances of those. That is how you can get a finite subset. You cannot get a finite subset otherwise. And if that finite subset does not have a model, then it means that you lift it back to phi, there is a finite subset of phi which does not have a model, right. So that's what happens here. Hence, there is a finite subset of phi which does not have a model, which contradicts our assumption that every finite subset of phi has a model.
So actually, it would have been if like G phi, then it would have been.
No, think of what happens when you go back from G sco phi. So, you take a finite subset of G scope phi which does not have a model. Okay. When you go back from G scope phi to phi, or when you go back from G scope phi to find the appropriate elements in scope phi, what do you have? You have all universal quantifiers. Yeah, you have all universal quantifiers, and you have found an instance for which that universal quantifier is not satisfied. So, that finite subset of scope phi is not satisfiable, because it is all the variables are universally quantified. That scope phi would have come from a finite subset of phi, and so what you are saying, and that might have its existential quantifiers, but if there is not, what we know is that if there is not a model for the ground term, then there is not a model for that subset too, right. So, that is how this works out. Yeah. So, okay, a simple, therefore, the interesting thing now about since I was talking about countability and uncountability, now it therefore it's therefore very clear that, so there is this important theorem by Löwenheim-Skolem which says that if a set phi, and this set phi could be infinite, has a model, then it has a model with a domain which is at most countable, right. So, this set phi, of course, again this set phi satisfies the same constraints, though I have not mentioned it here, as the compactness theorem. So, which means phi is going to be closed sigma formulae, there are no free variables, right. So, and what we are saying now is that if you are limited, therefore, what the Löwenheim-Skolem theorem essentially says is that if you are limited to a signature which gives you at most a countable number of terms, okay, then any model of a set of closed formulae of a countably at most countable of a denumerable set of closed formulae, it is not necessary to look among the uncountable sets. It is sufficient to look within the countable sets, which essentially means that therefore, you need the limitation of a finite or a countable sigma to produce only a countable number of terms is not actually a limitation for closed formulae. The moment your formulae become open, then the whole theorem crumbles, right. So, as far as closed formulae are concerned, which means that if you are looking at very general purpose theorems, even about things like the real numbers without the assumption of an uncountable number of constants, for example, if you are looking at very general theorems which are let us say universally quantified formulae, then they do have denumerable models if those theorems are true, right. So, they do have denumerable models, and it is not necessary to search through an uncountable set, and those denumerable models are essentially constructible from your signature. Yeah. And okay, so let us just quickly look at the proof. This is actually a very simple proof, but it is philosophically it has a great deal of influence. I mean, what it shows is that we are not particularly limited, even if we are talking about the first order theory of the reals. If you are looking at the first order theory of the reals and you are looking for theorems which are of a universal nature, then you are not limited by a language which is only countable and therefore cannot represent all of the reals. Yeah, that is actually the important consequence of this. So, let us look at the proof. So, assume phi has a model, right. Then scope phi has a model, the Skolemized version of phi has a model by theorem 26.7. What is it? So, it has a Herbrand model, that is basically Herbrand's theorem. So, it has a model if and only if it has a Herbrand model, and every Herbrand model has for a finite or countable signature, it has only enumerable number of terms, right, and the term language itself is the domain, right, and that is countable, that is a countable set, right. And so, if it has a model, if and only if the SCO-phi has a model, and that is at most a countable number of formulae, and therefore, this set of closed formulae phi, even if it is countably infinite, it has a, if it has a model, then I am not constrained if I just look for terms within the Herbrand universe. Yeah, I can find a model essentially in the Herbrand tree of interpretations, right. So therefore, phi has a model with at most a countable domain. There are extensions of the Löwenheim-Skolem theorem actually to uncountable signatures and finding uncountable models and so on and so forth, but I think they are not of a practical significance really. Our main concern when we look at uncountability is really in things like the reals and complex numbers. So, what happens in the first order theory of reals, what happens in the first order theory of complex numbers? There the theorems are not open, they are always closed formulae, and you are looking at, and if you have to find examples or counter examples, which is what models are about, right, examples are counter examples, then you are not constrained by the fact that you have only a countable language, a countable domain. You can construct your Herbrand terms for the models or counter examples from a countable language itself, from a countable construction. Okay. So what Herbrand's theorem and therefore Skolemization, Löwenheim-Skolem theorem, all of them, they essentially say is that for any theory, that any first order theory at least that I am interested in, I do not need to have any concrete models, I need to have only a language of terms. If I am interested only in the theorems of closed formulae, right. So the fact that you need to limit yourself only to a language of terms essentially therefore makes it possible to look at first order logic theorem proving and therefore logic programming and so on and so forth as feasible entities which you can work with just in a linguistic framework. You do not actually require full mathematical frameworks. You have a simple linguistic framework, and within which you can do your programming, you can do your theorem proving, and for most of the closed formulae, not necessarily the open formulae. Yeah. So, for open formulae, of course, there are going to be limitations, and in fact, the expressibility of various theorems is going to be there. But closed formulae, including existential formulae, actually can be done entirely within a countable language, which can be freely generated by a grammar, and that is actually the moral of the story, and from which the whole concept of theorem proving or logic programming for first order logic actually comes. Right. So, in this yeah.
In this statement of the theorem is phi of closed formulae.
Yeah, this phi is of closed formulae. Yeah, if you have open formulae, you get into trouble. Yeah. So actually, what what happens is that if you have open formulae, then your that Herbrand tree of interpretations is not sufficient for all the ground terms, for all the ground instances. This is sufficient just for the closed formulae. Okay. In this, so if you are going to do things completely linguistically, then clearly one of the most important things that we need to worry about is the notion of substitutions. And basically, you look at your ground instances and so on and so forth, all of them actually deal with substitutions. So, what I will do is I will quickly go through the theory of substitutions and take it for granted in future, yeah, basically. So, and this lecture basically on substitutions and instantiations is going to be independent of logic, because the notion of substitutions and instantiations is extremely general, and whatever we say here is done from a purely universal algebra framework, and of which your first order logic language is also just a certain term algebra in a universal algebra framework, right. So, it does not matter whether we are talking about the lambda calculus, the combinatory logic or first order logic or whatever, or even propositional logic with substitutions of meta variables by propositions. You take any algebra, essentially any term algebra, and you need to perform substitutions, and first order logic is no exception. Yeah. So, we will look at the substitutions and substitution theory in essentially a completely general framework, completely removed from first order logic, and as far as this theory is concerned, it is just first order logic is just another term algebra in which the theory of substitutions can be applied. Yeah. So, that is so. Okay, so the slides are not completely well prepared for this lecture, because it's a write up which I have just imported straight into this thing for my for the purpose of this lecture. So you will see certain discontinuities and so on, which I will clean up later. Okay, a substitution theta, as far as we are concerned, is a total function. Okay, in fundamental to everything, every term algebra, which also includes first order logic, is the set of variables V, right. And a substitution is just a total function. I am a total function from the set of variables to the set of terms, and this is here the important thing here in the case of a substitution is that it is almost everywhere the identity function, which means that you have an infinite collection of variables V, but there are only a finite number of variables which you are actually replacing by terms. All other variables just retain their identity. So, the effect of this, there is no effect of the substitution to all other variables. So, that is what I mean by almost everywhere identity. This almost everywhere is a technical term used in first order logic to say that used in second order logic to essentially say that in all except a finite number of cases. Yeah. So now what we are saying is, so there are only a finite number of variables which are actually replaced by some terms which are not the same variable themselves, and so this we will call the domain of this substitution. By the you should not confuse this. You should not confuse this DOM. This is some DOM, right? Where have I written? So
omega is the signature.
Huh?
Omega.
Omega is the signature. Yeah. So so I use this DOM, small DOM, to denote only those variables which are being replaced by other terms other than themselves. So, all those variables y for which theta of y is just y itself, I am excluding from this. So, remember that theta is a total function. So, as a function, its domain is the whole set of variables and its codomain is the whole set of terms t omega v, but this small DOM essentially gives you this finite set of variables x I such that theta of x I is different from x I. Yeah. So, that is what here. So, look at this, theta is represented as a finite set t for x, where theta of x where t is different from x. Yeah. So, that is the theta, and corresponding to DOM you also have this concept of a range. Yeah. So, range is just this set of terms t which act as the image of the variables which are actually being replaced. Okay, so, there is this identity substitution. The identity substitution of course, is the identity function from variables to variables itself, and therefore, its domain and range are both empty. Its DOM and range are both empty, in that the small DOM and range. Okay, in general, let's skip this because it is not relevant to first order logic, but maybe you should read it. We have this usual notion of admissibility of a substitution for in a term or in a predicate. So far all the substitutions that we considered in first order logic were substitutions of essentially a single variable by a term. But what I am doing here now is I am generalizing that notion to a set of possible variables by a set of possible terms, and this is what is known as a simultaneous substitution. It is quite possible that I have a substitution theta which replaces x for y and y for x, right. Okay. So, if I have a term let us say f of x y, then the notion of simultaneity of application essentially means that theta of f of x y is equal to f of y of x is simultaneous and not sequential. There is no particular order, it is actually simultaneous. So, you look at all the occurrences of variables which have to be replaced and replace them simultaneously. So, that whereas, if there was some sequence you applied here, then you will most likely get f of x x or f of y y, you will not get f of y x, you will not be able to switch terms, right. So, the notion of simultaneity is important, and the notion of, and along with the notion of simultaneity also comes the notion of admissibility, which needs to be generalized from a single term for variable substitution to a set of possible substitutions, simultaneous substitutions. So, but the basic principle in admissibility still remains the same. You do a simultaneous substitution and there should be no capture of free variables. That is the basic principle on which it is defined. So, in a more general fashion, what we are saying is that so a substitution theta which replaces a set of variables, let us say x 1 to x n by a respective set of terms t 1 to t n is admissible if each of the substitutions in that set is admissible, right. Okay. Then we have the notion of application of theta to s, which is what I said. What I have given, so it is by induction on the structure of substitutions. It has to be simultaneous, but what I have also taken into account is the possibility that you might have bound variables occurring in terms. This is something that we did not actually think of it in first order logic. In the logic of terms, in the language of terms of first order logic, there were no binding operators. I mean, this treatment being general enough has to take into account the fact of binding operators. So, these capital O x is like a typical binding operator. Think of it as either a quantifier in first order logic, or think of it as lambda x in lambda calculus, for example. So, what happens to substitution? So, it is defined by induction. Yeah. Okay. So, the basic facts about substitutions are that they are size non decreasing. The effect of a substitution can never reduce the size of the abstract syntax tree on which it is applied. Yeah. It has to be either size expanding or the size remains the same. The size remains the same when you are, and this is because you are replacing a single variable which is a leaf node of an abstract syntax tree by a term t, which is a tree in itself, right. So, the only way the size can remain the same is if you replace a variable by another variable. In all other cases, the size will be increasing. Yeah.
So could you repeat the binding operator?
So, as I said, this whole theory of substitutions, it is not, it is meant to be generally applicable in a universal algebra framework. Yeah. So, in general, if you had if you have an operator with its own parameterized on a variable and having a scope, which is what happens in the case of quantifiers, it happens in the case of lambda and the lambda calculus, lambda abstractions, then what does the notion of an applying a substitution mean in that case? Basically, if any substitution of that bound variable cannot result in any substitution, because the variable itself, it is just that there is a coincidence of name in the substitution and in the binding, but actually the two variables are different, right. I mean, this, what I am saying is, if x belongs to the domain of theta, okay, that means in theta there is a replacement for x by a term t, and I am applying this theta to a binding term of the form some operator x s prime, then clearly this x in the binding is different from the x mentioned in the theta, and therefore, the effect should be that this bound x throughout does not change in any way. So, what it means is that you remove that particular substitution t for x out of theta, treating the new substitution theta prime as one which leaves x unchanged, and apply that to the body of this s prime. That is all that I am saying. All I am saying is substitutions when pushed in through a binding operator should not affect that bound operator, should not affect that binding in any way. Yeah, they do not have any effect on that binding. Otherwise, for all other variables they actually push through, right, through the terms, which in the terms of when you are looking at abstract syntax trees, what you are saying is when you apply it from the top to the root, they actually filter down to the subtrees. It is like applying the substitution uniformly down till you reach the leaves and then make the replace the leaf by a corresponding tree t. Yeah. Of course, if that leaf is x and x has a binding up there in the syntax tree somewhere like this, then what you are saying is, so let us take the same theta. I have some syntax tree with x occurring here and maybe a x occurring with in a binding. So, basically what we are saying is this entire subtree is in the scope of this x. So, if I apply this theta on this tree, then this theta at least can have no effect on this x, on any of the, on any part of the subtree which has x in the leaf, theta cannot have any effect. On the other hand, if you look at this, so that means this y for x has no effect on this subtree because x is bound. On the other hand, x for y is not admissible even if there is no binding for y, because of the fact that by replacing y for x I might be capturing a free occurrence. So, this substitution theta has no effect at all on this subtree, but if there is some free occurrence of x here, then essentially theta will percolate down and replace this x by y, for example. Yeah. So, these are some basic the important, I mean these are not intuitively very hard to understand, but they are something that when you have to program them you have to be careful. Where does the binding take place, and therefore, how does it percolate down, what is the effect. So, the effect of this, so here of course, there is a problem of admissibility, because of which x for y cannot be done, but so you have to take care of both admissibility and bound variables. One possible the natural thing to do is to use alpha conversion, right, in which case what will you do, you will replace this x by let us say a brand new variable z, which means this x becomes z here, and now this x for y becomes admissible, and so any free occurrence of y will get replaced by x, but that x will continue to remain free. Y for x, because of the fact that there is no free x here, y for x has no effect. Yeah. So, those are the things. So, we use alpha conversion quite intensively in all this to give uniqueness of names, to distinguish bound variables from free variables and so on. Okay. So, the basic fact of life here is that substitutions are length and are depth and size non decreasing, and then we have the usual notion of a ground substitution. If all the terms which are being substituted, so if you have a set of substitutions, simultaneous substitutions T I x I, and all the T I are ground terms, then you think of, then it is a ground substitution. And you also think of common instances. So, if I can, there are two terms or there are two or more terms T 1 to T n, which as syntax trees do not look alike, but if there is a substitution which can be applied uniformly to all of them, so that the resulting trees look identical, then you will say that that resulting u is a common instance of these terms. Yeah, I am sorry, there is not a single substitution, there is actually a sequence of substitution, there is a corresponding set of substitutions theta 1 to T n theta n, such that you can make all these trees equivalent to the look the same as u, then you say that u is a common instance. Yeah. This is slightly different from that of unification, which we will come to. Okay, so, two terms T and u are called variants of each other if I can find two substitutions theta and tau, such that theta applied to one of them gives me the other and tau applied to the other gives me the first one, right. But more often we will not be looking at two different substitutions. What we will be looking at are so I can take this, I can look at substitutions. So, this was simultaneous substitutions, but I can compose simultaneous two different simultaneous substitutions together, in which case I have a composition operation on substitutions which I need to define. Yeah, the effect, and basically it is defined by its effect on this on that term. So, so essentially, so supposing I have two different substitutions theta and tau, and for a given term t I first apply theta. So, I get a new term t prime, and then I apply tau on t prime, I get a new term t double prime. So, the effect of doing tau after theta is the composition. So, what is the composite effect of, what is the substitution which can be considered the composite effect of two substitutions, yeah, performed in sequence. So essentially this composition operation shows that substitutions are closed under composition, and there is a huge amount of case analysis, but so this composition is essentially this. So, I have so tau composed with theta, I am just using, since they are like function composition, I am just using the function composition operation. So, this is a new substitution chi such that now what you need to do is you need to look at the DOMs of theta and tau, and since you are performing things in sequence, that you have to actually perform this. So you take, so you separate out those which are not in the domain of theta, separate out those variables which are not in the domain of theta, which means that any application of theta will not disturb those variables. So, if those variables have to be disturbed, they will be disturbed only by tau. Okay. And so this second addend here, the second component of this union essentially tells you that all those variables which are not in the domain of theta get replaced by whatever tau specifies for them. Yeah. And if you look at variables which are in the, so now look at the variables which are in the domain of theta. So, theta will first replace each of those xi's by some term si. That si will then has its own collection of variables which tau will again replace some of them, right. So, that is equivalent to actually taking tau applied to each of these terms si and replacing xi by tau applied to si. Yeah. And this is for all the xi's which are in the domain of theta. For all the xi's which are not in the domain of theta, you just take the appropriate substitution from tau, and this tj yj is just a substitution from tau. Yeah. And this union, because notice that this is the domain of these two substitutions is disjoint. So, the union is the composite substitution, and that is the effect of composing tau with theta. Yeah. And essentially what this means now is, supposing theta and tau were such that their domains were disjoint, then their composition will be exactly the same as taking the union of the two. Yeah. Okay, if their domains and ranges were all completely disjoint, then the composition will just be the union. Otherwise, you will have to apply this tau on each of these si's. So, that is right. Now, if you look at substitutions themselves as an algebra with a composition operation, then the substitutions actually form a monoid. Yeah. So, you take any signature omega, you take an infinite collection of variables v. So, and you take the set of all possible substitutions, let us say some capital S, set of all possible substitutions on this, that itself forms a monoid with this 1 as the identity element. And the composition of substitutions is associative, that is something you can prove, and you have a very nice structure like this. Yeah. Notice that I am making yeah.
What is a monoid?
A monoid is a set which is with a product operation which is associative, and there is an identity element. Okay. So, the natural numbers are a monoid under addition, for example, yeah, with 0 being included in the naturals. Yeah. Take any set of take any alphabet, the set of all strings forms a monoid with the empty string being the identity element. Yeah. It is not abelian. The natural numbers under addition are abelian.
And it is not necessary that there is an inverse.
Yeah, it is not necessary that there is an inverse. Yeah. So, that is so the inverses may or may not exist actually. So, yeah.
In your exercise 28.3, what is the second condition?
Oh, this is the associativity.
In the exercise,
Oh.
domain of tau,
Oh, okay.
second condition.
Basically, this domain of theta intersection domain of tau is empty, and domain of tau intersection free variables of t, all t's which belong to the range of tau.
Should it be range of theta?
Yes, I think it should be the range of theta. Okay, so there is clearly a mistake there. Huh? Domain of tau intersection, yeah, I think it should be the range of theta. Yeah, I think it should, because we are looking at a tau composed theta being just the union, right. So, this has to be theta definitely. Thanks, I will correct that mistake. Yeah. Okay, notice that I am making a clear distinction between the monoid equality and syntactic identity. Yeah, and it's most books do not do that, and it makes it quite confusing sometimes. Okay, so so this is so okay, so they form a monoid, and then there is a notion of, let me see now. This may not be very important for the rest of this lecture. So, let us skip this business of pure variable substitution. You can actually go and read it yourself. The most important thing is, I mean, there are too many theorems there, which okay. Yeah, so let us actually, so this is the notion of substitution which we want. I do not think we require all these notions of pure variable substitutions and substitution chains. There are lots of interesting things you can prove, which we will skip for the moment. But the more important thing is how are we going to use this notion of substitutions, couple it with the notion of Herbrand, with the consequences of the Herbrand's theorem and the Löwenheim-Skolem theorem, in order to come up with essentially a programming mechanism. Yeah. So, basically we need to be able to define this, we need to be able to use this notion of substitutions to find what is known as a correct answer substitution in a logic program. And so, we will work our way now towards essentially the theory of logic programming, because that is what Herbrand's theorem gives us. The Löwenheim-Skolem theorem also gives us that to look for models, you need to search only within a countable language of terms, you do not need to go any further. Yeah. So, I have rushed through this notion of substitutions, but please go through it somewhere, but it is really ancillary, but we need to know the notion of composition of substitutions, and we need to know the notion of simultaneous substitutions in order to be able to, because in order to be able to actually deal with the notions with what is known as a correct answer substitution in logic programming. Yeah. So, go through it and we will start that next time. Yeah, I will stop here.